Good afternoon, everybody. So yeah, I'm going to be talking about porting a couple of libraries that I presented last year to use AudioWorklets. Some of the problems that I kind of ran into, and some of the things that made it easier than I initially thought it was going to be to port them. But first, where those libraries were is they were using the script processor node, and as many of us know, for a long time the script processor node ran with everything else in the main thread, which for me was awesome. I loved this. I abused this so badly. I did so many things that made absolutely no sense coming from like the perspective of somebody who's done audio programming in C, that it was just incredible the things that I was able to do, and that meant things like stochastically changing the entire audio graph from one sample to the next inside of the audio callback. Crazy things. It was super fun. But of course, the reality is that the script processor node, in the end, it broke my heart because you have this extra latency that gets added to it. You have the interrupts that happen from all these other processes that happen inside of the main thread. So as convenient as it was to do everything in one thread, and as much as I really valued that experience, I was super excited for AudioWorklets to come along so I could start doing things in a way that wouldn't incur these problems. So of course with AudioWorklets, we have these two kind of threads that they occupy. You have your main thread AudioWorklet node, and then you have your AudioWorklet processor thread. And you have to do all this kind of management of talking between the two. And in some cases, that can be pretty simple. If you know all the requirements for your signal processing ahead of time, you can just define all your signal processing, say what the interaction points are, and you're done. You don't have to worry about it anymore. The internet, the flow of information is basically unidirectional from the main thread, user interaction events going to the AudioWorklet, and that's it. But for more dynamic music programming languages, things get a little bit trickier because you're making new instruments on the fly, you're adding effects on the fly, you're programming new points for interaction on the fly, and everything has to kind of be reconfigurable. So the two libraries that I'm going to be talking about today are Genish.js and Gibberish.js. Genish is a collection of low-level unit generators for doing things like managing phase, handling buffers of data, and it's a port of the Gen language for MaximSP, a rough port. And Gibberish is built on top of that and provides higher-level synthesis objects and sequencing objects. And so the goals for this were to kind of maintain the features of the Gibberish and Genish in the script processor. So some of those are audio rate modulation for multiple schedulers, being able to think of time as a signal, more like what you would have in a modular analog synthesis environment as opposed to a set of discrete events. Being able to visualize algorithmic processes taking place in the audio thread, and using anonymous functions to do dynamic sequencing. And then most importantly for me was trying to keep the APIs the same, change as little as possible going from this single-threaded version to this multi-threaded version. And in the case of Genish, this was actually very simple because Genish kind of does follow this idea of you program the DSP once, you tell it what the interaction points are, and that's it. It's not really a reconfigurable system. So in Genish, here's a really simple example of making a sine wave with a single point of interaction, which is the param ugen. And param basically says, okay, we're going to store a floating point number in the memory heap, and we're going to store the index to access that floating point number, and then you can change that with just a tiny bit of metaprogramming. By changing the value property, it's going to go and change that floating point number. And then in the AudioWorklet version, instead of changing it directly inside the memory, it actually just sends a message across the message port to the AudioWorklet processor thread. The AudioWorklet processor thread has an API where it understands to change that address, and it gets updated accordingly. And now that shared array buffers are introduced, I'm not even entirely sure if that's still necessary. That's something I need to look into. And then in addition, inside of Genish, you can also hook it up as to interact with other web audio API nodes, and this is just a quick code sample of how to do that. But you can create an AudioWorklet on the fly and then immediately start connecting other web audio API nodes to it. So for Genish, it was actually pretty simple. There was just a bare minimum of stuff that was required. With Gibberish, it wound up being a little bit more complicated to do it. But here's some of the things the problems that you're kind of running into. So the solution for being able to do all these things that I wanted to do that I arrived at was basically maintaining mirroring of state between the main thread and what was happening in the AudioWorklet processor thread. So we need to communicate instantiation of new unit generators, communicate any changes to any property values, and this is a bi-directional thing because all sequencing and scheduling occurs in the AudioWorklet processor thread in order to make sure that they can be modulated at audio rate. So that has to go back to the main thread, and then user interaction events that occurred in the main thread and change property values have to be sent to the AudioWorklet processor. Communicate method calls and communicate UGen output for visualization purposes and analysis purposes. And so I wound up doing this, and it's not important to read this code, but I wound up doing this using ES6 proxy objects. And so the basic idea here is that we use proxies whenever you create a new unit generator, the value that's returned is a proxy object, and when you set a property on that proxy object or call a method on that proxy object, in addition to actually changing it in whatever thread the unit generator is currently occupying, it also sends a message to the other thread saying, call this method with this object, change this property on this object to kind of synchronize the state between the two. And the main reason I posted this kind of longer code sample is this is the entire proxy for the main thread unit generator. So it's a couple of dozen lines of code to kind of implement this system that automatically is sending method calls and property changes back and forth. And in the AudioWorklet processor thread, it's much shorter. I'm only sending the values when we're setting properties on objects. So it didn't actually take too much code to implement this idea of mirroring the state back and forth. And then we can get a lot of the features that I was trying to maintain, even when porting this to run in the AudioWorklets. And as I mentioned really briefly, one of the things that I'm also doing here is capturing the last computed value of each unit generator and sending it back to the main thread. And whenever you do this property setting and scheduling and sequencing in the AudioWorklet processor thread, basically what's happening is it's storing all the messages for that particular block of samples that's being computed, and then at the end of computing the block of samples, it sends all the property value changes along with the associated objects serialized back to the main thread. Okay, so what are some things where this did not work out so well? So here's an example of a code snippet that I took from a Gibberish demo from when it was using script processors. And basically what this little snippet does is it creates a closed hi-hat sound and an open hi-hat sound. Then it creates a function that randomly triggers one of them with different amplitudes. And then there's a sequencer that calls that function every 11,000 samples or so. And the problem with this is that I can take this function that I've created, the play hat function, and I can serialize it by converting it into a string, send it over the message port, and then use the function constructor to recreate it. But it doesn't capture the surrounding scope. So all the up values to the closure associated with the function are lost. In this case, the reference to closed hat is lost, the reference to open hat is lost, and this function is not going to work. So as a kind of a solution, I can do things like say, oh, I want to wrap the function and then pass the two objects to this wrap function that I've made, which basically adds an extra step of serialization to it and includes the object IDs of these things that I want to pass the scope of the function along with it. But at this point, I've basically failed in my goal of not changing the API, not forcing the end user to have to think about the multi-threaded operation that's passing. They're now having to say, oh, I need to specifically capture the closer with this function call and pass it. And maybe I could do something fancier with this last example where whenever I pass a function to a sequencer, I could analyze the code of the function, figure out what objects are being called on inside of the code, and then automatically serialize those along with the function to capture the scope. There's still things to try that I haven't quite gotten around to that might make it a little bit easier. And then even with this, yeah, there's more complicated types of dynamic sequencing, particularly in live coding performance. You have this idea of temporal recursions, redefining functions on the fly that are then going to be repeatedly called, that are going to be tricky to figure out how to implement precisely between these threads. So I'm going to show what some of this looks like inside of Gibber, which is a language that runs on top of Gibberish, and some of the types of feedback that can be generated. And I'm going to have to put the microphone down for this. And the important thing about these annotations and these examples that I'm showing is that they used to be opt-in in Gibberish. Oh, sorry. Well, I got to type in. What? Oh, just base. Okay. They used to be opt-in because they would interfere with the audio thread when I was running these annotations and visualizations inside of the main thread, the necklace. I've heard so much about it. I have no idea. Okay. Yeah. Maybe. No, this is. Okay. I did the best I could. For example, in this drum beat that I've just created, it might be a little bit hard to see, but again, all the sequencing and scheduling is occurring inside the AudioWorklet processor thread. In this case, it's sending the results of that sequencing back to the main thread, which is then able to highlight the symbols corresponding to the sample that's currently being played here. So let's do another example where I'm going to make a sine wave. And then I'm going to tell a synthesizer to play some notes. And it's going to choose the notes by sampling the sine wave every quarter note. So now we're seeing the sine wave, because I'm always sending the last output of all the unit generators back to the main thread, I can visualize the rounded sine wave, and it's also sending the points where it's actually selecting the samples from, so that I can visualize this as well. So basically, by using like a fairly terse set of metaprogramming, adding stuff to these proxies to just kind of pass the information back and forth, I'm able to kind of do these annotations, and now I no longer have to worry about it screwing up my audio thread. And I say that, but we'll see if that's actually true later tonight when I perform with this. You guys can all listen for audio interrupts if they happen due to garbage collection or whatever, and then tell me that I was wrong. So just to conclude, porting existing script processor libraries to AudioWorklets can potentially be fairly simple with a little bit of metaprogramming, but certain dynamic music programming concepts are going to present problems, and I'm looking forward to geeking out, trying to figure out how to solve some of them in the future. Thanks, and any questions?